Hello, Chem 1B. This is Chapter 18, Lecture Video 6, and we're going to be talking about the temperature dependence of spontaneity. So, when we look at the Gibbs free energy equation here that you see, we know that delta H and delta S both could be positive or negative, right? Depending on the reaction that is occurring. Now, that actually has an effect on how temperature will affect spontaneity. For instance, in this reaction here, if we look at this reaction, we have 2 moles of gas going to 3 moles of gas. This tells me delta S of my reaction is going to be positive. And I know because it's telling me that delta H of my reaction is negative. If we look at Gibbs free energy equation here, that means I have a negative number, something, right, minus temperature times a positive value. Now, it does not matter what number for temperature you put in here. The answer to this equation is always going to be a negative value. In other words, this system is going to always be spontaneous at any temperature, right? So this system is always spontaneous at any temperature, right? So this occurs when delta H is negative and delta S is positive. These are the two stronger driving forces of spontaneity, right? We want energy to be distributed across the space, which is what happens in exothermic processes, and we want the system to become more disordered, which occurs when our delta S is positive. So this system is always spontaneous, and that occurs when our delta H is negative and our delta S is positive. What if we have the opposite occurring, right? In this system, our delta S is going to be negative, and we know that our delta H is positive. I'm going to change colors here. So delta H is positive, delta S is negative. What's going on here then? Well, if we look at that same equation, delta G is equal to now a positive value minus T delta S, which is now a negative value. If we look at this, it doesn't matter what temperature is, this equation is always going to spit out a positive value. And we know that when delta G is positive, our system is not spontaneous. So this is never going to be spontaneous at any temperatures. Temperature is not going to matter here. And this occurs when delta H is positive and delta S is negative. Basically the opposite of our first scenario. Now, let's look at this next system, right? How does it work when both delta H and delta S are the same sign? In this system, delta S is going to be negative. We know that because we're going from a liquid to a solid. Now, our delta H is also negative. This means that temperature is going to matter here now because we have a negative delta H minus T times a negative delta S. This whole term becomes positive because a negative times a negative is a positive, which means that the larger this value gets, the more likely delta G will end up as being positive. The lower the temperature is, the more likely our system is going to be negative. What this tells me for this system is that at high temp, the system is not spontaneous. And at low temp, the system is spontaneous. Now, I don't have an exact number here, what temperature is low, what temperature is high. That depends on the magnitude of our delta S and our delta H. But at the lower the temperature is, the more spontaneous this reaction will be. And the higher the temperature, the less spontaneous it'll be. Which makes a lot of sense because we're basically melting water, right? Or sorry, we're freezing water. We're going from the liquid state to the solid state. Everybody knows you make ice in cold temperatures, not hot temperatures. So low temperature being spontaneous, hopefully this makes a lot of sense. This whole thing here occurs when delta H is negative and delta S is negative. But what if they're both positive? So in this scenario down here, we have delta S is positive and delta H is positive. Effectively, what we're going to see is the opposite of the previous example. because of this, right, if we look at our delta G equation, right, it's going to be equal to a positive number minus T times a positive value. Well, this whole term here is now negative. This is positive. As temperature gets higher, we're more likely to get a negative number from this equation. So at, high temp, we're spontaneous here. And at low temp, we're not spontaneous. Again, this whole situation occurs when both delta H and delta S are positive. And here we have, if we look at this system, right, liquid going to a gas, it's basically boiling water. When do we boil water? At low temperature? No, we heat it up. We got to get it to high temperature for this to happen. So hopefully that helps. We're going to continue going. If you have any questions, as always, contact me. So let's look at a clicker question that would have been on here. Which of the following systems will be spontaneous at high temperature and non-spontaneous at low temperature? Hopefully kind of a give me if you paid any attention to the last slide. And we have all 5 of these different options. E is obviously totally not the right answer, right? So this we can kind of just go, no, not that. It's got to be one where the signs are the same, because that's only where temperature actually matters as far as spontaneity. Like this one here is never spontaneous. And this one is always spontaneous. It's really, we got to pick between A and D. Which one it is, let's talk about, right? Remember, when both are positive, that was boiling water. So that's going to be high temperature is spontaneity. D is our correct answer here. Again, this is spontaneous. I'm just going to kind of start abbreviating that at high temp. This one's spontaneous at low temp. All right, so we know temperature plays a role, and if both the delta H and the delta S are the same sign, then at some temperature, the system is going to go from being spontaneous to non-spontaneous or vice versa. We can actually determine what temperature that's going to occur at, right? So let's look at O2 and N2 in our atmosphere. We're told they're stable with respect to NO. What that really means is we're not spontaneously forming nitrogen monoxide from nitrogen and oxygen because it's a non-spontaneous reaction initially. What temperature would we have to have in order for this reaction to become spontaneous, right? So this is the reaction we're talking about. You see that we have 2 moles of gas here going to 2 moles of gas here, but NO is a more complex molecule than N2 or O2, so this is probably going to have a delta S that is positive still. As you can see, it's just barely positive, but it's still positive. Now, the delta H for this reaction is also positive. This tells me that this reaction is more likely going to be spontaneous at higher temperatures than lower temperatures. Now, what temperature do we need to get to go from a non-spontaneous process to a spontaneous one? Well, we can use delta G is equal to delta H minus T delta S here to do this. Effectively, when is our system going to switch from non-spontaneous to spontaneous? Well, that's going to occur, the flipping point is when delta G is 0, right? So I'm going to take this and plug it into my equation. Then I'm going to take my delta H, plug it in, my delta S, plug that in, and now I can solve for temperature where this is going to flip. When are we going to, above what temperature are we going to become spontaneous, right? So if we do that, right, I basically can write out that equation, right? Now I'm setting delta G naught equal to 0. And I can rearrange this to solve for T, which is effectively delta H over delta S. Now, again, an important thing here, as always, is delta H is in kilojoules as given and delta S is in joules. We need to change one to the other. So I changed delta H to joules by multiplying by 1,000. And now I'm dividing these two. And if I divide them, I get that the temperature this would occur at, this flip from non-spontaneous to spontaneous, is 7,360 Kelvin. Now, we're assuming these two do not change here with temperature, and that's not entirely true. Over small temperature ranges, it's absolutely true. But in this case, this is definitely not a small temperature range, so we probably have some significant error in our calculation, but this is the way we're going to learn how to do it in this class because the alternative involves a lot of calculus. So it's a bad assumption in this case, but we'd still calculate it this way. And basically what we're saying here is that above this temperature, the reaction would become spontaneous. Okay, so if you have any questions, as always, email me or come to my Zoom discussion sessions.